This is end-to-end tracing in Ceph. We are Golsana Ghaemi, Oindrilla Chatterjee, Aditya Singh, and Bowen Song. We have been mentored by Mania Abdi, Raja Sambasivan, and Peter Portante. So, let's look at our problem statement. Firstly, Ceph is an open source, high performance distributed storage application. So, the existing tracing infrastructure in Ceph, which is Blockin, is fairly rudimentary and it's not continuously enabled. So, thus, this necessitates a replacement by an always on tracing infrastructure like Uber's Jaeger. So, to achieve this, we did the following. Firstly, we deployed Ceph on the OpenStack environment. Secondly, we compiled Ceph with Blockin and derived the Blockin traces. Third, we instrumented Jaeger on Hot Rod and derived the Jaeger traces. Fourth, after looking into the Blockin API and the Jaeger API and understanding the functions, we mapped a correspondence between them. And last, the Blockin API wrapped around the Jaeger functions to instrument Jaeger finally on Ceph. So let's look at the Blockin API. Firstly, tracing in Ceph is carried out as shown. The init, copy name, and event are the crucial functions in Blockin which carry out tracing. This is how a trace point is placed in the Ceph code. The ztracer namespace in Blockin consists of all the major functions which carry out tracing using Blockin. The init function is responsible for initializing a trace. It assigns span ID, trace ID, and parent span ID to a trace. The keyval function records key value annotations. The event function starts a trace and records timestamp annotation. Our research on the Ceph architecture unveiled a huge list of dependencies, very important to the tracing process, over which I'll be going through in a short and sweet way. Here is an illustration of the two most important functions in the Blockin API. As we see here, the trace init function in the object cacher cc file in Ceph calls in the ztracer namespace of Blockin, which further has dependencies in the zipkin cc files. After following through a layer of functions, it finally assigns the parent ID, the trace ID, and the span ID. As we see here, the trace event function in the object cacher cc file in Ceph calls the Blockin timestamp function in the ztracer namespace in Blockin. It further has zip dependencies in zipkin cc files, which further call the tracepoint functions present in the LTTNG backend. Before we move on to Jaeger, let's have a quick demonstration of deriving traces using Blockin and Ceph.
We clone Ceph source code and compile it with Blockin enabled for our goal, which is capturing traces from Ceph using Blockin. Virtual cluster is enough. This environment gives us 3 OSD nodes, 1 monitor node, and 1 Rados gateway as the client. Blockin, which is the Ceph tracing tool, uses LTTNG as its backend. So, in order to start tracing, we should create LTTNG session, enable trace points, and start the tracing session as you are watching in the video. Now is the time to work with Ceph again while tracing session is started. At this point, we face a problem. In order to solve the problem, we had to open another terminal and type this command that you are watching in the video. After we solve this problem, We wanted to make pool for storing data with the command make pool in the video that you will watch it in some seconds. After solving the problem, then we put the file we stored in the pool as the name test-object-1. Then with the ls command, we can see the list of files in this pool. Then with this OSD map command, we want to find OSD nodes that contain that object, test-object-1. Then we want to get the object from the pool, check whether it is correct, and finally remove it from the pool. After working with Ceph, finally we should stop LTTNG session. That's its way. Whenever you want to capture traces using LTTNG, you should start and stop it. And finally, you can see the traces using LTTNG view.
Let's go through certain important functions in the Jaeger API. These are the functions which are corresponding to the functions we just described in the blocking API. And these are the start span, the log, the make, and the tag functions. Let's look at a sample code to understand these functions of Jaeger.
Hello everyone. So in a couple of minutes, we'll be demoing to you the Jaeger traces that we've obtained. But before that, I'll quickly run you through the code behind. Firstly, what we need to do is we need to instantiate a tracer. And here we can see the class tracer being defined. And here we can see a span is being started. And so inject and extract. Now what do these functions do? So in order to continue traces over the process boundaries and RPC calls, we need a way to propagate the span context over the wire. And so inject and extract are these two functions that provide us these capabilities. Also, all the recorded spans have the same trace ID, which will be demoed to you soon. So next, what we need to do is annotate the trace span in this case with tags and logs. So here we can say that so essentially tag is like a key value pair that provides certain metadata about the span. It also describes attributes of span for the entire duration of the span. And on the other hand, a log consists of a timestamp and some other data. Next, let's move on to span context. So essentially, we can see here that span context defines these parameters of the span like trace ID, span ID, parent ID, etc. So it basically represents an immutable thread safe portion of the span that can be used to establish references or to propagate over the wire. So yeah, that was a quick run through of the code. Now we'll be demoing the traces to you soon.
Hello everyone, would like to show the traces for from Jaeger side. Over here we start the Jaeger from Docker so that on here we can visualize traces, and over this end we are gonna fire some Python little hello world application format and gonna do a little publish so that we can see traces from different components. This is a distributable application, and all the traces will be sent through HTTP by HTTP requests. And let's do the main function. Python 2 -m. Hello everyone, this is Jaeger, right? And as you can see here on the right hand side, the main application initializes the trace and starts build up some connections and start a span. You can see the span ID stayed constant throughout, and what's different is their child ID and whatever it is that's inside it. And you can see here where it goes through all of that to say Jaeger and then everyone, and then we get out of all those applications. And let's just see what is going on, because the description I just had, that was pretty bad, right? So let's refresh Jaeger, see if we get traces. Yeah, we have 4 here. And let's enter from the main trace main application. We can see hello world, and inside hello world we have formatters and publishers, and then all those informations are inside. Even tells which machine it is and its IP address, what kind of version it's using. This is very, very exciting. And of course, over here you can see how long the program took, and of course we will have a bit of a DAG picture, and yeah, so all the same thing. It's a little thing right here. So we could go to each one of them and to see what is really going on. But then again, you can see all of this information from the main application. And so that is that. Thank you. How do I close it? And now I would like to talk about implementing Jaeger on Ceph. Ceph itself is very big of a project, if you can see the size of it. It's a C++ based project, and the amount of code in there is just unparalleled. And its build file, it's already 29 gigs, so trust me when I say we spent a lot of time trying to make Ceph deployed on our VMs. Because of that, because of how big the Ceph is, we are limited to change only parts of Ceph instead of deploying the full Jaeger onto Ceph. We are not putting trace points on Ceph to avoid breaking Ceph itself. Instead, we are replacing the blocking function, which is the existing tracing functions that's on Ceph. And we focused on 4 of the functions, but I'll cover them later. Jaeger itself, library itself, Jaeger agent itself, it's also a bit of an issue to deploy on a CentOS VM. There are 3 main dependencies for a Jaeger client. There is a Thrift, is a message transmission protocol, and in the future, Jaeger promised to move to Protobuf by Google. And Jaeger is using YAML to do the data serialization in order to ship those data efficiently across VMs or across distributed systems. And also it is an open tracing based project. Now, when I say it's underdeveloped, I mean Jaeger C++ is still need some work. As I was talking to one of the developer for Jaeger C++, some of the errors actually because of some of the errors are just very hard for us to fix at this point, and parts of its core dependency updated, Jaeger will need some time to catch up with them, such as thrift, and we were told that Jaeger will make its advancement soon to upgrade to the 0.11 version of our project. Is put on a bit of the hold because of this problem. Now I would like to talk about our code changes. So on the left side here, the constructor init event and key val is based on the blocking tracing that already exists on the Ceph, and we are using Jaeger make, Jaeger start span, and the set operation name and tag to replace them. So let's take a quick look. So now let's take a quick look at the code. This is ztracer, which is also called blocking in the Ceph. It's the tracing mechanism for Ceph, and it's got a bit of a constructor going on, and init to start. Init the trace. We could call it parent trace, or just init the trace, and this trace could be a child of some other traces, and we could put in some key val information in that trace, and also record timestamp for some big events happening. And for a parity, we did the exact same swap. For to construct a trace, we used the trace Jaeger make function, and then to make a trace. The init is mapped to Jaeger starting a span, and that span we are putting in logs or set operations for the key val and event functions, and of course these are timed functions. So that's the implementation side, and hopefully we will get the debugging done by the end of the project. Thank you.
The next steps are as follows. Once we get rid of the problems that we are facing due to the dependencies, we'd like an effective replacement of code, and thus we'll know if ripping off the block and trace points is necessary or not. Once Jaeger is instrumented on Ceph, we'd like to do a performance analysis to see if we are adding an additional performance overhead to Ceph due to Jaeger, and thus minimize the trade-off. We would like to talk about what we did gather from this project. Firstly, always-on traces are very essential for any tracing infrastructure. Having to stop and start the system again is not a very effective mechanism to trace a system. Secondly, deployment of an open source software like Ceph has been very challenging due to a number of reasons. And thus we would like to do our best to give back to the open source communities our learnings and gatherings from what we have performed in the last few months. Thirdly, installing Jaeger has been particularly tedious too. This is a part and parcel of an open source software community, and I know that the community stands together during such desperate times as we saw on various discussion platforms. Yet we feel that there is a need for better documentation for stable releases of a software, and we wish to contribute towards the same. Any infrastructure implemented must have a decent documentation for future developers. A lack of any kind of documentation and layered implementation of functions in block-in was quite a setback, which was overcome after a lot of efforts. So we urge contributors to effectively document the interesting work that you do for the open source community. And that is all. Thank you so much.